In this video we're going to look at the nucleophilic addition reactions of aldehydes and ketones. If you've forgotten about nucleophiles, you might be worth going back to look at nucleophilic substitution of halogenoalkanes and just remind yourself about the properties of a nucleophile. So a nucleophile is an electron pair donor. It has a pair of electrons that it can donate, and it donates that pair of electrons to a delta positive carbon. So why would that be possible in aldehyde and ketone? Well, we know that oxygen is more electronegative than carbon, and so we have a polar bond. And the presence of that delta plus carbon means that the aldehydes and ketones are susceptible to attack by nucleophiles. Nucleophile attacks the delta plus carbon and forms a new covalent bond. And addition then happens across that double bond. So you're adding things to the C and to the O, and you're getting an addition reaction. So we're going to divide these up into a couple of sections, and in this section we're going to look at the reaction that leads to the reduction of aldehydes and ketones, and we're going to look at the conditions and the reagents that were used to achieve that. So when we reduce aldehydes and ketones, they're going to get reduced to alcohols. So if we have a primary alcohol, that would have come from an aldehyde, and a secondary alcohol would have come from a ketone. It's going to occur via the nucleophilic addition mechanism. Now our reagent is called sodium borohydride. Okay, so we've got a hydride ion in there. Hydride ion is a H- ion, and it's that H- ion that's going to be our nucleophile, our electron pair donor. And the conditions that we're going to be using are that we're going to use this in aqueous solution. It's really important that we remember that condition. So remember, for organic chemistry, if we want to do oxidation, we use O in square brackets, and if we want to do reduction, we just can use H in square brackets to simplify the reagents that I used for oxidation and reduction. So we're going to take our general equation for an aldehyde. Remember, aldehydes have an R group and then a C with a double bond O and a H, and we write it like this with CHO. We're going to put H in square brackets. So just taking it, we know we're going to make an alcohol, so we're going to be adding hydrogen across the double bond, so one to the carbon and one to the oxygen. So 2 hydrogens in total are being added, so we're going to need to balance that with 2 in front of our reducing agent. Aldehydes are reduced to form primary alcohols. Remember, if you've forgotten how to classify alcohols, you could go back and look at your alcohols notes. Whereas ketones, which have our C double bond O in the middle of our chain, they're going to be reduced to form the alcohol group in the middle of the chain with 2 R groups attached to the functional group carbon, the carbon with the alcohol, and therefore we're going to be forming secondary alcohols. Remember, we're adding hydrogen across the double bond, so we're adding a hydrogen to the carbon and a hydrogen to the oxygen, adding it across the double bond. So pause the video now and have a go at balancing these equations and naming the alcohol that you have formed. So if we have a look at these examples, we've got propanal. It's a 3-carbon chain aldehyde, and it's becoming propan-1-ol. It's really important that you get these numbers in the alcohols, because remember, there is something called propan-2-ol, and it wouldn't be made from reduction of propanal. Butanone makes butan-2-ol. Cyclopentanone doesn't need a number because it's a symmetrical structure, and cyclopentanol similarly doesn't need a number. Just be careful, because when we use skeletal formula like this, we don't show that hydrogen that we've added to the carbon where the alcohol group is attached, and so we might be tempted to forget to balance our equation properly. We just need to be careful that we balance our equation properly. 2 hydrogens, one on the oxygen and one on the carbon. You just can't see the one on the carbon in a skeletal formula. So how does this happen? Let's take a look at the mechanisms, reminding ourselves that curly arrows must start from a lone pair or a covalent bond, because we know that a covalent bond is a shared pair, and that is because curly arrows show movement of a pair of electrons. They show the direction of the movement of that pair. Now the name for this mechanism we mentioned at the start of this video is nucleophilic addition. And And although the reagent is sodium borohydride in aqueous conditions, the nucleophile is just the hydride ion. Now hydride is a H-, so the hydrogen's got a full shell, 2 electrons, and so it has a minus charge. Let's have a go at how that happens. We're going to draw ethanol. Let's draw 2 carbon chain with a double bond O and a hydrogen, and then saturate this other carbon with its hydrogens. There's our structure of ethanol, and here is our hydride. So our first curly arrow is going to go from a lone pair, so curly arrows must start at a lone pair or a shared pair, from a lone pair, and it's going to attack this carbon. Now the reason it picks that carbon is because oxygen is more electronegative than carbon, and so that bond is polar. What happens then is the pi bond, the second of the double bond, breaks and moves the electrons onto the oxygen. So we're not losing anything, it's not substitution, we're adding the H- and just breaking that bond. Nothing is lost. So we haven't done anything to this methyl group at the end, so just copy that out. But we have turned this oxygen into an O with a minus charge and a lone pair. We moved a pair of electrons that were in the pi bond onto the oxygen. The hydrogen's still there, and we added a hydride ion, so the pair of electrons that was the lone pair is now the shared pair in the bond. So what happens now is that this lone pair here is going to go and pick up a hydrogen from the aqueous solution, from the water. So it's going to go and grab a hydrogen, and the bond in the water molecule is going to break to release that hydrogen ion. And we're going to get CH3, C with an OH and 2 H's, that's our structure of ethanol, plus a hydroxide ion is going to be left over at the end. So the hydride ion is adding, breaking the double bond, and then the O- is using its lone pair to pick up a hydrogen atom from the aqueous solution. See if you can apply that to propanone with sodium borohydride. Remember, the sodium definitely doesn't appear in our mechanism, no metals in mechanisms, and we're using sodium borohydride as a source of hydride ions. So if you've had a go at that, you should have got something looking like this. Watching out, make sure your curly arrow goes from a lone pair or from a bond, from a lone pair or from a bond in each of these steps. And we've made propan-2-ol. So again, have another go, see if you can do this with pentan-2-one with sodium borohydride. So pentan-2-one with sodium borohydride. You should have got something looking like this. Check your answers, make sure you're happy with everything that you've drawn.